Welcome to this video about lubrication fundamentals. I'm Roland Larsson. I will discuss a little bit about how a lubricant film or lubricating film is formed in a hydrodynamically lubricated bearing. It's a two-part video, and let's start with the first part. The content of this video is first we ask ourselves why lubricate, and afterwards I will discuss hydrodynamic lubrication, and I will talk about something called a wedge mechanism, and I will probably say the word load carrying capacity a number of times, and that means how much load will this bearing carry under certain circumstances. And I will also discuss load speed and viscosity and how that affects the load carrying capacity. So why do we lubricate? Well, the answer is maybe obvious. We want to separate the surfaces from coming in contact with each other. We want to reduce friction. We want to reduce or totally stop wear from occurring, and we definitely want to prevent tribological failures like seizure and scuffing and gulling. But the lubricant has also other roles in a system. It also is there to cool the surfaces. It protects the surfaces from corrosion. It can prevent contaminants to come into the system, and it may clean the system also. But here we will concentrate on the first one, to separate the surfaces from coming into contact. So, starting with hydrodynamic lubrication then, and different bearings. These are two typical bearings we are showing when we are discussing hydrodynamic lubrication. The left one is a kind of a theoretical linear bearing, which we are using to demonstrate mechanisms, while the right one is a journal bearing, which is very common in a machine. Of course, it's in both cases you have something which we could call a wedge. So I just try to draw that wedge here now. So the wedge is showing the importance here in both bearings, is that the bearing, the film, which is the yellowish here in the picture, the film becomes smaller or thinner as in the direction of motion. So the surface move here in the linear bearing, the lower surface moves while the pad is stationary. In the journal bearing, the journal rotates in this direction while the housing is stationary. And in both cases, you can see if you follow the motion here, you see that the film thickness, the distance between the two surfaces becomes smaller and smaller as in the direction of flow. And it's the same for this linear bearing. We call this the inlet, and we call this the outlet. And you see that the inlet is bigger than the outlet, and in both cases we form a kind of wedge. And before talking more about wedge mechanisms, I'm just showing an example here from industry, and that's from a hydropower plant in northern Sweden. It's a pretty big hydropower plant. I believe this could be maybe 100 tons weight of the rotor, and the only thing that separates the rotating part from the stationary part is a thin oil film in the truss bearing, which is inside this one. So the truss bearing carries the whole load of the machine and separates it from the stationary part of the machine. And I guess in this case the lubricant film thickness is something like 50 micrometers. So it's a very, very thin film that separates this very heavy machine from disaster, really. If this machine comes in contact with the other surfaces, you will have a catastrophe, of course. So this is coming back to the theoretical wedge bearing, the linear bearing. Just some definitions on this picture now. We assume it has a length. So in the hydropower plant case, it's something like 1 meter. We have a load, of course, an applied load. That could be the weight, or it could be some other loads applied on the bearing. It has a film thickness h as a function of x. So h, as I said, the inlet is bigger than the outlet, and you should now remember here now that the film thickness is very much smaller than the length of the bearing. So as I said, this is something like 50 micrometers, while this is 1 meter. So you see that there is a gigantic difference. But still we are drawing the bearing like this just to be able to illustrate things inside the oil film. So this angle theta here is also a very small number. It's normally much less than 1 degree, even if it's in this picture is shown with several degrees. Important is also that one surface is moving. Both surfaces may move, but there must be some motion, otherwise you can't bring in any lubricant into the bearing. So before saying any more than that, you can sit back a little bit, pause the video, and think about this question then. Which of these two bearings carries the highest load? Is it the one with a thick film in the left on the left side, or is it the one with the thin film on the right hand side? So which one of the loads FA and FB is the biggest? Stop the video for a while. In order to answer the question, I will discuss the mechanisms of hydrodynamic lubrication and the wedge mechanism. In mechanics, we have two laws that must be obeyed. Those are, first of all, the force equilibrium. There will be a pressure in the lubricant film, and that pressure must balance the applied load. Secondly, there is a need for flow balance or flow continuity. The lubricant that comes into the bearing in this inlet end must be the same flow that goes out. So the flow in must be equal to flow out, and it must also be the same flow in each intersection here along the bearing film. Now remember, this is a model bearing, and so it's infinitely long bearing. So but it's the same for a finite length bearing too. The flow in must be the same as flow out, even if the flow can also flow out in the direction towards yourself and away from yourself. We also have two types of flow. The first flow is Couette flow, and that is surface-driven flow. So it's the flow driven by the moving surface. When the surface moves here, it will bring in lubricant, and we assume that the oil is sticking to the surface. So the lubricant molecules closest to the surface stick to the surface and move with the same speed as the surface. We also assume that we have a Newtonian fluid, and the film is very thin, and of that reason we get what we call a Couette flow profile. So up here, where on the stationary bearing pad surface we have no speed, and in between those two surfaces we assume a linear distributional speed, which is correct in this case. The other type of flow is Poiseuille flow, and that is pressure-driven flow. And that pressure-driven flow comes from the assumption that we assume, or we must have a pressure inside the film, otherwise we can't separate the surfaces. So inside here we have a pressure, and that pressure will want, of course, to squeeze out or to force the lubricant out from the contact, and it forces it out in both directions, both towards the outlet and towards the inlet. And putting those two flows together explains how this flow balance or flow continuity can occur. So first of all, if we only would have Couette flows, we see that the flow into the bearing is bigger because the total flow is actually the area of this triangle. So since the film thickness is bigger here in the inlet, then the flow into the bearing is bigger than the flow out from the bearing, and that is not allowed according to the flow continuity law. So how do we do that? Well, then we have the pressure-driven flow, the Poiseuille flow, and the Poiseuille flow actually forces some of the fluid to flow back in the negative direction, while in the outlet it flows in the same direction as the Couette flow. So that means that it reduces the flow in the inlet and increases the flow in the outlet, and it reduces the flow in the inlet that much that it actually becomes exactly the same flow in the inlet as in the outlet. So on this picture, which I try to draw, it's a little bit tricky actually. You see that the flow profile now is a little bit shaped like this in the inlet and shaped like this in the outlet. But the idea here is that the area should be the same here as here. And that means that the pressure inside the film is actually formed in such a way that to create this flow balance in every intersection here, it should be the same flow. So that means that you get a pressure that looks something like this, a pressure distribution that looks something like this. It is zero here where you have atmospheric pressure in the inlet and outlet, and it reaches a maximum somewhere inside the bearing. And inside where you have the maximum here, you don't have any pressure gradient that can push out the fluid from the film. So at that position you only have Couette flow, but this Couette flow profile is the same, giving you the same flow as in the inlet and in the outlet. So those two natural laws, they work together with different types of flows, and they balance each other perfectly and creates a pressure that normally and many times is big enough to fully separate the surfaces and create a very good lubricant film or lubricating film. Okay, that was the end of part 1. So just take a break now before you start listening to the next part of this video. Thank you very much.